Hi, welcome to Teardown Tuesday. Yes, it's retro time again. We do love retro and we do love the 80s, or at least I do. We have a classic Sinclair Pocket TV, also known as the FTV1 for flat TV1, or sometimes the TV80. It's known as 1984 vintage. Beautiful. This was sent in by David Walsh from England as part of the previous mailbag segment. So thank you very much, David. And yes, it is the brainchild of Sir Clive Sinclair, of course. You may have seen my Sinclair C5 video which I've done, which I'll link in down below for those Sinclair aficionados. And this was a flat screen pocket TV, but more interestingly, it wasn't LCD, it was CRT, cathode ray tube. Yes, uses a flat CRT, and that's really what we're interested in, is how they've actually designed and constructed that flat CRT in this thing. I mean, inside, the rest of it is just, you know, some pocket TV circuitry, nothing exciting there, but this was a groundbreaking product for its day in terms of just, you know, being a flat screen pocket TV like this, having a decent size screen on it, and also getting a decent battery life. Rumour has it was around about 15 hours or something like that. Used another innovation, a flat lithium battery inside this thing. So, you know, that was really, it was novel in its day for a lot of reasons. So, you know what we say here on the EEVblog, don't turn it on, take it apart. And unfortunately, taking it apart is all we can do, because this one doesn't work. David tells me that he ripped the main IC out of this thing. There's a single chip which pretty much does everything, designed by Ferranti, which did quite a bit of Sinclair stuff, and he used that to build another one fully working. So normally it's got a few screws on here, but it only came with one screw in it, and telescopic antenna on this thing, of course, just you know, pretty standard, and not much else on it. There's an on-off volume control, there's a tuning knob down here, and there's a earphone jack on the side. So not much at all, but we're really fascinated by that CRT. And you'll notice that it is the screen looks to be at the base of the unit, the bottom of the unit, and it uses a lensing system on the top to see that. So that's going to be really fascinating to take a look at the construction of that. So let's take this thing, hopefully it should just pop off, and yeah, we're in like Flynn, and beautiful. Look at that. We can see the backside of the CRT tube in there, the flat CRT tube. So hopefully this just pops out like that, and isn't that a thing of beauty? Look at that. Oh, what a Bobby Dazzler. And of course we'll get into the CRT in some detail, but the first thing you notice, all through hole construction. Of course, this is you know, 1984. Who knows when actual development started on this. Main IC down there is actually socketed. That looks like it was production socketed, because I don't see any evidence of David actually ripping out that chip and putting in a socket. So he would have just lifted the main Ferranti chip out, which is a ZN401E. But it's all through hole. There's been some touch up done around here, but yeah, sort of, you know, classic double-sided through hole construction. They're done pretty well to jam pack it all into there, but pretty much the thickness of this thing was determined by the CRT. So once your design requirements have been set, you know, by the thickness of that CRT, of course, that's the driving force behind this entire thing, then you go, well, might as well use all through-hole components and just stand them on end like that. We've got our resistors on end like that, diodes on end over here. Looks like we've got our high-voltage multiplier up the top here. You can see that diode capacitor. Oh, there it is. Diode capacitor arrangement like that. So that's our voltage multiplier tucked up in there. We've got a plastic rubber boot on there, so we'll take that off, just protecting that, and that is the main CRT mechanism. So there's not really much else exciting in here. There's like a worm drive type mechanism for the tuning There's a speaker on the end which is just mounted into a cutout in the board. There's a couple of adjustment trim pots which would have been adjusted during production testing. Couple more on the front there. Looks like we've got a screened RF can over here. And, well, you know, not a huge amount to it. Nothing mounted on the back, of course. And, but all the interest lies in that CRT. And you'll notice one of the most interesting things is that this thing is, look, it is like a 16:9 aspect ratio. So this is like the world's first 16:9 pocket TV, I guess. And they've got, what they do is they put a Fresnel lens on the top of this to make it, to stretch it out and make it appear square like it was supposed to, like it was meant to be. So that is just a way to make the screen look bigger while reducing your need to actually deflect your beam in here a large way and keeping it to a more compact size. So that's a novel way to do it. This was quite common back in the 70s, for example, with LED displays. You get, you know, tiny 7-segment LED bubble displays, and they'd have a lens on top to make the LED segments appear bigger than what they actually were in real life. But that is quite a work of art. I like that. Unfortunately, this thing was a pretty much a commercial flop. David says that the batteries for it cost a fortune, which is one of the reasons that it actually failed, because the batteries weren't rechargeable. They were lithium disposable flat batteries. And really the only thing of note in the tuner section is this worm drive tune-in potentiometer here. So it's just a potentiometer. There's just 3 terminals on the back there. Where are they? There, and there. There we go. So they're the 3 connections for that potentiometer. And I don't know, those numbers probably correlate to the channels in the UK system. But this thing, you know, it was a reasonably capable tuner for this pocket size, that's for sure. And as I mentioned, we have our multiplier here. Once again, standard Cockcroft multiplier here, which I've done videos on previously, and that generates, there's various taps on that which generate different voltages up to 2400 volts for the screen grid in here, and then for the various other grids they just tap those off. And the final repeller version up here, I think, final repeller system up here, I think, which is about 1400 volts or thereabouts. So of course the real interest lies in this magnificently designed horizontal CRT, or flat CRT here. And yes, it works like a regular CRT, but as I'll explain, there's a third mechanism of deflection in here, not just X and Y. Now, of course, yes, like a regular CRT, this is a vacuum, of course. You've got an electron gun up here, shoots the electron beam through, and it hits the phosphor screen. In this case, instead of on the front, hits it on the back, as I'll explain. And of course, vacuum inside, there's the thing where they sucked out the vacuum and sealed up the tube down in there, and all of the connections are just taken. It looks like they've run across some conductive traces on the top glass part of the CRT up here, and they just run to through-hole pins down there. So just like a regular CRT, there's the electron gun, there's the grids, there'll be a heater in there, of course, there's the grids in there, there's 3 grids in here, your X and Y deflection plates, and what's called a repeller system in here to deflect your electron beam, which shoots out like this, deflect it then 90 degrees down onto your phosphor there. I think it's whiteboard time. And here's how the Sinclair flat screen CRT works. No, Sir Clive himself didn't actually invent this. Apparently the invention goes to a Dr. D. Gabor from some university somewhere. But let's take a look at a regular CRT, very briefly, electrostatic CRT here, and I've gone through this in a previous video which I'll link down below as well. So I'll briefly cover it. So electrostatic CRTs are what you'll typically find inside and oscilloscope, your old analog oscilloscope like this. And your TVs work with electromagnetic deflection, and it all has to do with how they deflect the electron beam here. Instead of using electrostatic plates like this that you apply a voltage to, a typical TV uses magnetic deflection coils, so it'll have the big yoke around here and it magnetically deflects it. But you know, it basically works the same. Now, the reason they use electrostatic deflection in the Sinclair one is that, well, it's very simple and very small and compact, well suited to small screen displays, and that's why oscilloscopes use them, because oscilloscopes typically have a relatively small screen on them, and they're quite long like that. So you basically, with electrostatic deflection, you only get relatively shallow deflection angles, but as we'll see, that's what we need here in the Sinclair CRT. Now, the way it basically works is you've got your electron gun here with your cathode heater that generates your electron beam shooting out, and then you've got three control grids here, control screen, focus grids. There's various ways to make this sort of stuff work, but we won't get into the details of that. And then, as I said, the X and Y deflection plates, which then deflect your beam across the screen. In terms of a CRT, of course, it's scanned in lines, and the Sinclair CRT, just like a regular TV, has 625 scan lines. Depends on the standard it's actually using, but it can have 625, which is quite remarkable on a little screen like that. But that's pretty much all there is to it. So it uses what's called two-stage deflection, X and Y plates. But of course, the disadvantage is it has to be very long like this, a huge tube like this, and the electrons, when they hit the phosphor screen on the front, they have to travel through the screen. And what all this adds up to, the bigger screen you have, of course, the more power is required to deflect the things, and also you have to compensate for the loss of the phosphor dot actually going through the phosphor material on the front. But let's take a look at the flat screen Sinclair system. It works basically up until the screen part here exactly the same as your regular CRT. You've got an electron gun with your cathode heater, shoots out your electron beam, you've got your three grids in there, and you've got your X and Y deflection plates. It works exactly the same. But in this case, instead of a flat screen at the front, it's horizontal end on, so it can be made really flat like this. And you saw it in the unit, it's like less than an inch thick, really quite good. Even though the screen isn't very big, the fact is it's flat. Now, when it comes in like this, the beam, of course, can be scanned across the surface. The phosphor screen, in the case of the Sinclair one, is on the back. There's that blue dotted one there, as you saw in the physical construction, mounted on the back of it. So that gives us the instant advantage of not having to for the light to travel through the phosphor material. So we've already got a gain there in terms of power efficiency. Sinclair claim 3 times the brightness of a regular CRT at 1/10 the power. So that's very impressive, and that's in large part due to the fact that you're seeing the phosphor on this actual side that the electron beam hits the phosphor. It doesn't have to pass through. There's no loss there. So it's on the back like that. But if you just had that, okay, you can actually deflect your beam like this, X and Y, and you could scan across there. But unfortunately, the what we'll call, say, the Y deflection here will hit this screen at a very, very shallow angle. So you're not going to get that nice sharp a dot that you're used to in your on your regular CRT. It's just going to hit it at a really shallow angle, and it's just going to be ruined. So what they do is they bend or use a 3-stage or a 3rd-stage deflection. It's called a repeller system, and they basically, the rear phosphor screen, that's a positive potential, and then they have a transparent electrode on the front here, which is made out of tin oxide. So you've got 2 plates there, so a 3rd set of deflection plates. And when you've got the high enough voltage on there, in this case it's about 1400 volts, then when the electron beam shoots out, when the electron shoots out like this, then these plates here actually deflect it again at 90 degrees, so it hits 90 degrees bang on like it does in a regular CRT. And that's how you can construct a flat CRT in that sort of form factor. You just need that third deflection plate. So this is all very clever, and I really like it. And as we'll see in the unit, it's they haven't used a 4:3 aspect ratio screen on here. They've actually used a widescreen format aspect ratio in this direction. So this thing isn't, so the screen is actually more like this, like that, because, so it only uses this active area in here like this. It just means that you have to, well, sorry, it'll be on the back phosphor screen here that's the case, so that they don't have to deflect the beam as much in this direction like that, because that requires extra length, extra power, extra voltage. You're not going to do that. So they've designed it to be a rectangular widescreen shape like that to minimize the angle required on that deflection. And of course, this one here, this Y plate doesn't have to deflect much in and out like that. It's a tiny little shallow angle. So really, this whole thing is designed to get the shallowest deflection angle possible, and then you can get by on much lower voltages and lower power. And that rear phosphor screen, because it's got the repeller on there, it hits straight on like that, just like it does, and it works on a regular CRT. So it works just like a regular CRT. I'm sure there's a bit more, physical science and, tweaking going on to actually perfect this, to actually get it right. But once you've done that, it actually works pretty well. And then because you've got that widescreen format like this, you don't want your image to be squished down into a wide format when it's designed for a 4:3 aspect ratio. So what they do is they just add a Fresnel lens on top of this, which, as we've seen on the thing, and that just stretches the image in this direction like that, and bingo, you end up with your 4:3 aspect ratio. So that is the very clever Sinclair flat screen TV. Now, Sinclair weren't the only ones working on this system. There were other players as well. Sony were another major one who had a similar sort of flat screen system. And this one's only mono, of course, much more difficult to perfect full color RGB into such a system. So if we go back to the CRT here, we can see all of the things in there. Here's our electron gun assembly here, and then we've got our 3 grids there. Can you see them? We've got 1, 2, 3, 1, 2, 3 in there. Really, that one I think is, yeah, that's folded. 1, 2, 3 grids in there. Not sure of the exact construction of those, and you can see that these 2 connections here are the horizontal. Well, no, in this case, well, these are the plates that deflect it in this direction here. Whether or not you want to call that horizontal or vertical depends on your orientation. And you can see that that's folded, that metal is folded inside there. If we have a look at the bottom, you probably see that better. There it is. Aha, there we go. There's our 2 separate plates. So the electron beam comes out of there, goes through there, and then is deflected in that direction or that direction by those 2 plates under that 89 there. I don't know, 68, whatever that is. Don't know what that marker means, but there's those 2 plates, and then you can see the other 2 plates. So the other orientation, 1 top, 1 bottom. So you can see it there quite clearly. It looks like a little horn sort of coming out of there, but they're not actually. They're physically, electrically isolated plates, of course, 1 positive, 1 negative, and they're your deflection plates that deflect the electron beam across the front here. But of course, if you just had those, if you just had your X and your Y deflection plates like a regular electrostatic screen, then of course your electron beam, yeah, you could scan it across there, but it would hit at some sort of angle and you wouldn't get a nice solid dot on there. So what they've got is this transparent, well, this glass on the top has a transparent tin oxide coating, as I said, so you can actually see through it, but it acts as a deflection plate. And you can see the, look, you can see the signal going in there. You can see one of the connections going in there, and the other one is probably that one which then maybe goes under the bottom, or yeah, it connects to the bottom plate down in here, which contains the phosphor on that. So what you're seeing is the electron beam just reflected off the phosphor, or the phosphor emitting the light, the phosphor emitting the light directly, so it doesn't have to go through the phosphor like it does on a regular CRT, so you don't get the loss there, and then it has to come through this transparent tin oxide coating. I'm not sure what sort of loss you would get by going through that, but it looks pretty darn clear to me, so that's quite impressive. But that is technically a conductive plate on there, and there's the connection to it. There's the electrical connection. So that one is operating at about 1400 volts, that top part of the assembly there. In fact, I can see it. If I get the right angle, I'm going to have to get the right angle of light here. Sorry about the reflection off the roof, but look, you can see that. Look, there's the shape of the transparent tin oxide coating. You can see it, or plate, sorry. So it's actually shaped like that. So there it is. It's transparent, sort of. I don't know how they deposit or etch that on the glass or whatever. Some sort of process. Somebody will probably know out there, I'm sure. But that is really neat. I love that. And then that, of course, these two plates, this is the repeller system, which then directs the beam coming in at a not so good angle like this, a really shallow angle, actually deflects it directly down so that you can get the spot like you do on a nice sharp spot like you can on a regular CRT. So that really is quite novel. I love that. And of course it's the sort of widescreen format like this, because then you don't have to deflect the thing as far. It's all a trade-off in terms of size, power, and physical size and power consumption to drive that. So that's why they got the Fresnel lens on the top. It really is quite novel. I love it. I mean, they could have done away with the Fresnel lens, but then it would have been physically bigger, and I don't know how much extra power would have been required to actually push that through, but like to the different angles. But it's all going to be a big design trade-off, so it was probably better to design it as a very narrow screen like that, widescreen in this direction, of course, not going to be in this direction like this. So that one was just easier for them to design. It was easier just to deflect small angle like that, and of course small angle in that direction as well, or if it's center, very tiny angles we're talking about there, and that's why they can get away, including the transparent system, no loss going through the phosphor, get away with such low power and get 15 hours from a battery for a CRT system. Oh, incredible. Oops, sorry, I think I may have got that wrong. This connection here is the one to the top transparent tin oxide repeller plate, and you can probably get the right angle on there. You'll be able to see that it actually connects to these 2 points here. They've got 2 connection points, maybe for reliability perhaps. So there you have it. That's the Sinclair TV80 or FTV1 as it's known, and an innovative product for its day, but as with a lot of, quite a few Sinclair things, a commercial failure. Unfortunately, they only made about 15,000 of these units, and the batteries, of course, were expensive for the thing. Yeah, it could accept external DC charging on it. There it is. There's a DC jack down in there, but whoop-de-doo. Why have a tiny little pissant thing like this operating off a plug pack? It was all about the battery operation, and they were just too expensive. It was a flop. And of course LCDs were Casio and others were working on LCD at the time, and they just killed it. So really, this was an innovative product that had a very short lifespan because it was beaten by LCD technology. In this case, it was just almost obsolete before it came out. I think I read somewhere that Sir Clive spent £4 million and I think 6 years developing this thing. So yeah, so that was a fantastic little invention, and a lot of construction magic, a lot of production magic going into the CRT, this flat CRT here, but ultimately a commercial flop, which is a bit of a shame because it's just a thing of beauty. Look at that. And here's the schematic, which you can download with the link down below. And, as you can see, there's not much in it. It's all basically all single IC. There's the ZN401E from Ferranti. There's the tuner module up there. The tuner's actually got some SMD parts in there. I forgot to mention it's not all through hole. So that's a little RF tuner module can. There's the actual wire that came into the RF module. It was just stuck on the back there like that, just running down there. That's a little bit crusty, not much thought put into that, but basically, yeah, you've got your one IC pretty much decoding and controlling everything. Of course, down here we've got our high voltage generation. There's our step up transformer, and then we've got our voltage multiplier here, which, as I said, gets a couple of taps out of there. There we go, 2400 volts, 1920, 1440. So as I said, there's 1440 volts there. That should be going over to, yep, you can't quite see it, but that will be going over to the repeller over there. They sort of chopped that off. If we have a look at the CRT down in here, we can see the deflection plates here, the X and Y, but in this case they call them F and L frame and line plates. And then we've got our three control grids here. We've got our signal coming in here from our video amplifier up in there. There it is. It even tells you video amp. And of course we've got our heater, our electron gun, and that spits the beam out there. And there's two other pins in here which do a bit of magic, which affects the picture quality as well. This is the IPS pin, or the interplate shield in there, and this is the guard band, GB guard band pin here, and these affect the astigmatism of the electron beam and the overall picture quality. So there's tweaking going on there in terms of getting the best picture quality in this physical form factor. Interestingly, this was drawn in 1986, so by G. Kernan. I wonder if he's watching the blog. Could be. Anyone get in touch with G. Kernan? That'd be fantastic. Basically that was a couple of years after this thing was released, and I don't think it had that sort of lifespan, but obviously, a later revision to the schematic. All hand-drawn, of course. Beautiful. And interestingly, the line scan signals are derived from the switch-in power converter over here. So it is, quite a novel arrangement to actually drive the line scanning stuff from that. I don't know if that was typical in CRT TVs or not. I'm not really in that field, no pun intended, but I think that's quite novel. That's pretty much all she wrote. These things aren't a basic CRT, TV tuner basically isn't hugely complicated. I mean, once it's all in a single IC like that, and you can generate your voltages for the CRT, Bob's your uncle. So thank you very much, Dave, for sending that into Mailbag. That is absolutely awesome. I love this retro stuff, and I love Sir Clive Sinclair. Bit of a legend, really. How can you bag the guy? He really did some cool stuff, even if they were commercial flops. I love it. Now, as always, all of the links to the schematic and the theory of operation of this stuff, I will link in down below as well, so you can download that, the service and operation manual for the thing, and some other links. And as always, if you want to discuss it, the best place to do it is the EEVblog forum, because the YouTube comment system now sucks ass. And if you like it, as always, please give it a big thumbs up. Catch you next time.